Today we're going to look at two of the basic physical concepts behind thermohaline circulation. Two of the principles that we're going to focus on is difference in density and temperature causing movement of water, and the rotation of the Earth affecting the circulation via the Coriolis effect. These two principles combine to create a very complex system in our oceans, but let's just scratch the surface. We'll look at melting ice cubes and how different temperature and density water combines, and we'll also look at some rotational forces. Differences in density inside the world's oceans drives this circulation, pushing water all around the planet. Let's look at melting ice cubes in three different glasses, one with cold water, one with hot water, and one with salty water. As the ice cubes start to melt in the cold water, we should be able to see the solution mixing. You can see plumes of color coming off the ice cube, but they seem to be sinking to the bottom of the glass. In the salty glass, it's easy to see a very distinct pattern. From the large difference in density, the fresh meltwater is staying at the very top. In the hot glass of water, it's difficult to see any distinct pattern because the ice cube is melting so fast and the large difference in temperature is causing mixing to happen very quickly. What should be happening in the glass of hot water is that the cold, dense water is sinking to the very bottom and causing a convection current within the glass to mix the dye. In the cold glass, where there is not a large difference in temperature, there should be more consistent mixing and no convection current present. In thermohaline circulation, a large difference in density between waters in the North Atlantic causes deep water formation, where water sinks below the surface. This denser, colder, saltier water sinks down below fresh meltwater from Greenland. This experiment is so interesting because it shows that such a simple physical concept can be the cause and determining factor in a very complex system. If we look at some of the simple physical math behind the melting of ice, we can see that it really breaks down into two sections. These two most important sections are the gradients of temperature and density. If we understand these gradients in temperature and density, we can do some very simple calculations to get exact numbers about the amount of energy required to melt the ice and even the time it will take to melt a certain diameter of ice cube. Now let's take a look at some of the simple math behind this phenomenon. Today we're going to look at a simplified version of the equation used to determine the strength of thermohaline circulation. It breaks down into smaller components where we can see already that temperature and salinity play a major role. Let's look at each of the terms. K represents the hydraulic constant. Rho is representing density, which we then break down. Rho naught is a standard reference density. We can break rho down into further smaller components. This equation shows it broken down into a thermal expansion coefficient multiplied by a difference in temperature, otherwise known as the temperature gradient, as well as a haline expansion coefficient and a difference in salinities. These two terms combined make up density. Now let's take a look at some of the spinning forces that are involved in creating the Coriolis effect. As this die spins on a turntable, we can see distinct patterns forming in the water. The circulation is pushing the die into spirals, similar to ocean gyres, but the Coriolis effect is all about scale. Let's look at some of the simple math behind it. At its core, it's a force. So if we look at force equals ma, then we can break it down into further components that apply to the Coriolis effect. We use the rotation vector, the velocity relative to the frame of motion, the position vector, and the acceleration relative to the frame of motion. But the key to the Coriolis effect is about scale. So let's take a look at the Rossby number. This is the ratio of inertial force to Coriolis force, which determines whether or not there's an effect on a system. It takes into account the length or scale, the velocity of the object, and the Coriolis parameter. Things aren't always so simple, and we can see, even in this demonstration, how small changes like adding an object or changing the shape of the bowl can cause large-scale effects. But at the core, it's important to remember that these huge complex systems can be broken down into small, manageable parts that we can easily calculate. Thanks for listening.